You've probably heard before about the Fibonacci sequence. It's the pattern of numbers you get when you start with 1, then 1 again, and then add up the previous two numbers to find the next one in the sequence. So after these 1s comes 2, then 2 plus 1 is 3, 3 plus 2 is 5, and so on. When you first learn about the Fibonacci sequence, you'll often hear what's billed as a sort of strange and mysterious fact about it. If we look at the ratios of each consecutive pair, the second divided by the first, we find that they seem to be approaching some limit. In fact, as we go further and further out, the ratio of terms gets closer and closer to this exact value. 1 plus root 5 over 2, denoted with the Greek letter phi, otherwise known as the golden ratio. This fact is often presented as a mystical curiosity and without explanation. But in this video, I'd like to delve into that mystery and show that it's not actually all that mysterious. Instead, there is a beautiful and geometric way, based on linear algebra, to explain the relationship between the Fibonacci numbers and the golden ratio. Let's begin with the basic algebraic definition of the Fibonacci sequence, which asserts that term n plus 2 is the sum of the previous two. I'd like to write this in a slightly different way. Rather than looking at one number at a time, let's look at pairs of the form a sub n plus 1. How can we move that pair one position forward in the Fibonacci sequence and get to a sub n plus 1, a sub n plus 2? For manipulating pairs of numbers, the natural tool to use is a matrix. So let's look for a matrix which will take the vector a sub n plus 1 and turn it into the vector a sub n plus 1, a sub n plus 2. If we make the top row of this matrix 0 and 1, that sorts out the top component of our result vector. Now think about the bottom. If we write two 1s in the bottom row, then the bottom component of the result will be a sub n plus 1, and that is, by definition, a sub n plus 2. So this simple matrix, which we'll call A for the rest of the video, actually encodes the entire Fibonacci sequence. If we multiply it against the vector 1, 1, we get 1, 2. Multiplying it against 1, 2 gives us 2, 3. Doing it again, 3, 5, and so on and so on. Now it may seem like we've just overcomplicated things, because we already had a formula that described the Fibonacci sequence. The advantage here, though, is that a matrix is more than just a set of numbers to add and multiply. A matrix describes a transformation of space. All of a sudden, it lets us start to think visually and geometrically. So let's graph the sequence of points that come out of this matrix, one by one. We start with 1, 1, the first two numbers of the Fibonacci sequence. Applying A, we end up at 1, 2. Next come 2, 3, 3, 5, 5, 8, and 8, 13. Remember, each point here represents a pair of two consecutive Fibonacci numbers. There are a few things that we can notice about this set of points. First, they don't lie perfectly on a line, but it seems like they're very close to it. In fact, it's possible to draw a line that looks like this, almost as if we were doing a linear regression. But unlike a linear regression, in which we would expect some random noise, there are very definite patterns here. For example, the dots seem to switch regularly between different sides of the line. The difference shrinks very quickly, but you can take my word that the pattern continues if we zoom in. Also, the further we go, the dots seem to get closer and closer to the line. What's really interesting is that if we pick any other starting point, the exact same thing seems to happen. Let's suppose we defined a new Fibonacci sequence that started with 0, 2 instead of 1, 1. Applying the matrix A, we end up at 2, 2, then 2, 4, 4, 6, 6, 10, and 10, 16. It's a completely different sequence, but the exact same visual properties still show up. The points still close in on that same line while bouncing back and forth across it. We can shine some light on the situation by remembering that, first and foremost, a matrix describes a transformation of space. So instead of looking at what A does to individual points, let's draw a grid and visualize how this matrix distorts the entire 2D plane. I'll also leave in the yellow line from before as a reference. After one application of A, our 2D plane looks like this. Space seems to flip over on itself, and at the same time, everything gets squeezed in along the yellow line. Let's apply the same transformation again. Another flip, another squeeze. Over and over, we see space getting wrapped up and compressed in one direction, then stretched out in another, almost like a baker rolling out a long piece of dough. Every starting point tends towards this magic diagonal. Let's reset and watch that again. It may be easier to follow if we add a vector and watch what happens to it as we apply A over and over. As space transforms, it takes this vector up and to the right, pulling it in toward the yellow line. Now, here's something really significant. What if we choose a vector that's directly on the diagonal line to begin with? As we apply A over and over, it simply stretches in the direction it already points. This will turn out to be a really important idea. If we want to understand how this matrix works, it's a good idea to understand this particular vector and how it changes over time. Ultimately, our Fibonacci matrix just scales up this special vector v by some amount. So, v must satisfy this equation. Lambda here is just some scalar, a singular number that represents how much v scales up each time. It's easiest to try and find lambda first. We can transform the equation to look like this. Subtract lambda v from both sides, and then note that scaling v by lambda can also be written as a diagonal matrix. Then, subtracting two matrices just means subtracting each individual entry. Now we need to use a bit more linear algebra. A matrix can only send this vector to 0 if that matrix's determinant is 0. To find the determinant of a 2x2 matrix, we multiply the diagonals and subtract. And that leaves us with an expression we can reduce into a quadratic equation. This particular equation doesn't factor, but we can always solve it with the quadratic formula. There are two possible solutions here. If we take the positive branch of the square root, we get lambda 1 equals 1 plus root 5 over 2. In other words, the exact value of the golden ratio, about 1.618. If we take the negative branch, we get lambda 2 equals 1 minus root 5 over 2, which is about negative 0.618. Now remember, lambda is supposed to describe how the vector we saw earlier was scaling. So which of our two values fit? Let's go back to the picture. Remember, each time we applied A, v grew larger and stayed pointing in the same direction. This means that the scale factor has to be positive and greater than 1. In other words, our scale factor has to be lambda 1. What about lambda 2 then? It's not just some extraneous solution that we can ignore. In fact, there's another vector whose behavior it describes. Take a look at this blue vector here. After applying A, it flips its direction and shortens, but still lies along the same line as the original. Applying A over and over again, we see it flipping back and forth, always along the same line, always shrinking. This is precisely what it looks like to scale by lambda 2. The fact that lambda 2 is negative means that we reflect the vector each time. The fact that its absolute value is less than 1 means that its length shrinks. Now, we've done a lot, so let's pause for a second to do a quick recap. We started off by writing a formula for the Fibonacci sequence in matrix form. Then we looked at how that matrix would affect all of 2D space, not just the points for Fibonacci numbers. We saw that there were two particular directions of vectors that it behaved very nicely on. This vector, let's call it v1, scales by a factor of lambda 1 when we apply our matrix. It stretches in its original direction. This other vector, v2, scales by a factor of lambda 2. It shrinks and flips. Knowing the lambdas, we could look back at our equations and do a bit more algebra to solve for some actual coordinates for v1 and v2. But I'll save us some trouble and tell you that they turn out to be 1 lambda 1 and 1 lambda 2. We call v1 and v2 eigenvectors of A. That is, vectors which are just scaled up or down when you apply A. But how does this help us understand the patterns we saw at the start of the video? Well, let's say we pick a starting point like 1, 3. We can think of it as being made up of two different parts. A bit in the direction of v1, plus a bit of v2. When we apply A to this vector, we can think of it acting on the v1 and the v2 components independently. We know that the v1 component is going to grow. We know that the v2 component is going to shrink, and also flip its direction. Transforming those two components, we end up at 3, 4, exactly the result we would have predicted from doing the matrix multiplication directly. This also goes for every other point in 2D space. They're all made up of part v1 and part v2. After applying A, the v1 part is going to grow, and the v2 part is going to shrink and flip. If you repeat this process enough times, you'll eventually be left with pretty much only v1. This is why every starting point seems to move toward the yellow line we saw at the start of the video. All points approach closer and closer to the direction of v1 as the v2 component grows smaller and smaller. Now, we can finally answer the original question we posed at the start of the video. Why does the ratio of terms in the Fibonacci sequence approach the golden ratio? We produce each new point in this graph by applying the matrix A to the previous one. And the slope from the origin to each of those points is nothing other than the ratio of two consecutive Fibonacci numbers. But we also now know that applying A over and over brings every vector closer and closer to the direction of v1, reducing any little component of v2. So the further we go, the more precisely the slope to each point matches the slope of v1, which is exactly the golden ratio. So as we go forward through the Fibonacci sequence, the ratio of successive terms tends to exactly that limit. I love this explanation because as much as it answers an outstanding question, it also prompts us to ask new ones. The moment we understand how a matrix can describe the Fibonacci sequence, we can take that understanding in a lot of different directions. For example, can you derive the ratio of successive terms for a different sequence, like this one? Is it possible to come up with a rule for a sequence that results in eigenvectors that both grow, or both shrink, unlike the ones we saw here? Or how could you analyze the so-called Fibonacci sequence, where you sum the previous 3 terms instead of 2? I encourage you to play with some of these questions and others like them on your own. There's a whole rich world of mathematics out there to explore, and I'd love to hear your results in the comments. Happy investigating, and again, thanks for watching.